Alright guys, today we're going to solve a dynamics problem, problem 417. It reads, two projectiles, each with a mass of 10 kilograms, are fired simultaneously from the 1 megagram vehicle shown, which is moving with an initial velocity v1 of 1.2 meters per second in the direction opposite to the firing. Each projectile has a muzzle velocity vr of 1200 meters per second relative to the barrel. Calculate the velocity v2 of the vehicle after the projectiles have been fired. Alright, the first thing we're going to do is identify the variables we know. We know the mass of the vehicle is 1 megagram, which we know is equivalent to 1 times 10 to the 6 grams, which we could rewrite as 1, or actually 10 to the 3 times 10 to the 3 grams, which would be equivalent to 1,000 kilograms. Okay. Next, we know the velocity, initial velocity of the vehicle is 1.2 meters per second. How fast it's moving with projectiles loaded into it. We know the mass of the projectiles themselves are each 10 kilograms. We know the velocity of the projectiles after they're launched, after they're shot, is 1,200 meters per second. And finally, we try to find is our V2, our velocity of the vehicle after it's fired the projectiles. Alright, now I'm going to draw a sketch of the vehicle before and after firing the projectile. So we have our vehicle here. It has projectiles loaded into it. It's moving with initial velocity v1. We're going to designate going to the right as being positive, going to the left as being negative. So then we have our sketch of the vehicle after this. It fires projectiles. So we have our vehicle down here. It shoots the projectiles. With a muzzle velocity, they tell us of 1,200 meters per second. So we'll just rewrite that as velocity of the projectile with respect to the vehicle. It's how it's fast and moving relative to the vehicle at that moment. We have our V2, our final velocity of the vehicle after it's fired the projectiles. And so I'll go ahead and draw this as a projectile here. Its velocity. Now, in order to solve this problem, we're going to have to use conservation of momentum. Conservation of momentum. Okay. So, conservation of momentum tells us that the initial momentum in the system is conserved, and it's equal to the final momentum in the system. The initial momentum in the system is equal to the total mass of the vehicle and the projectiles multiplied by its initial velocity v1. The final momentum in the system, when they're separated, is equal to the mass of the vehicle multiplied by its velocity of the vehicle v2, plus we have two projectiles, so 2 times mass of the projectile multiplied by its velocity, absolute velocity that is, relative to the Earth. So how do we find this absolute velocity of the projectile relative to the Earth? Well, we need to examine, based on our diagrams, what we have. We have our velocity of projectile relative to the Earth. It's going to be equal to the velocity of the projectile relative to the vehicle, which we have, plus the velocity, these are vectors, of the vehicle itself relative to the Earth. We know
now that our velocity of the projectile relative to the Earth will simply be equal to our muzzle velocity, which is VR, moving to the left, which is the negative direction, combined with our velocity of our vehicle after the projectile has been launched, which is our V2, which is positive, moving to the right. Therefore, we substitute these numbers in, and we know that our velocity of our projectile relative to the Earth is simply going to be equal to negative 1,200 meters per second plus our velocity of our vehicle after the projectiles have been launched,
V2.
We can now substitute in our velocity of our projectiles relative to the Earth, the absolute velocity, into our equation for our initial and final momentum being conserved, and then solve from there. So, down here, we know that our initial momentum is going to be our total mass multiplied by V1, and that's equal to our mass of our vehicle times velocity 2 after its projectile has been launched, plus 2 times the mass of the projectiles, because there's 2 of them, times our absolute velocity is V2, we range this, minus 1,200 meters per second. All right, so from here, it's simply a matter of substituting our values into our variables and solving algebraically. So our total mass before the projectiles are launched would be 1,000 kilograms for the cart, the vehicle, plus 2 projectiles, so 2 times 10 kilograms. Okay, and this is all multiplied by its velocity for initial momentum of 1.2 meters per second. This is equal to the mass of the vehicle, which is again simply 1,000 kilograms, multiplied by V2, plus 2 projectiles, so 2 times mass of each projectile, which is 10 kilograms, times V2, our velocity of the cart after the vehicle after it's launched, projectiles, minus 1,200 meter per second velocity of the projectiles themselves. Okay. So now we can go ahead and solve this.
We have 1,000 plus 2 times 10, which is 1,020, times 1.2, which gives us 1,224 kilogram meter per second. There's no simpler unit for momentum. That's equal now to 1,000 times V2 plus 2 times 10, should be 20 times V2, so 20 V2, minus, this would be 20 times 1,200, so we have 20 times 1,200, which is 24,000, so minus 24,000 kilogram meter per second. So we can add this 24,000 over. So we have 24,000 plus 1,224. We get
25,224. We have 25,224 kilogram meter per second equals, combine these two, we get 1,020. 1,020 times V2, divided by 1,020, and our final velocity of the vehicle
after it's launched the projectiles is going to be 24.7
meters per second. So very much larger speed than initially had after firing projectiles.
All right, thanks. Be sure to like and subscribe. Appreciate it.